This is a key for the assignment on different force equations. So I'm going to go through each of these and kind of explain the strategy for using it. I will give you the equations on the exam. You just have to know how to plug in the numbers, and so make sure as you're going through you see some of the different things that I do here in terms of making sure things are in the right units and plugging things in the right way and things like that. So this first one is a gravitational problem. For that you need the general form of the gravity equation. Gravity, we've got Fg equals capital G, that's the gravitational constant, times m1, m2, those are the masses, over the distance between the two things squared. So plugging numbers in here, gravitational constant 6.67 times 10 to the negative 11th. The mass of these two objects, we've got 3.5 times 10 to the 19th. And then times 4.2 times 10 to the 15th. And then divided by the radius, that's 5 times 10 to the 10th. And then that radius needs to be squared. All right, so plug that into your calculator. You should get 3,922 newtons approximately. All of these are calculating forces, so you should be getting newtons for pretty much every single one. This next one here, talking about charge and some things, so hopefully that should clue you into the fact that it's an electrical force problem. So we've got Fe here equals K, that's Coulomb's constant, the electrical constant, times Q1 times Q2 over R squared. Again, the Q's here are the charge, and the radius is R, or the distance between the two objects is R. So it's very similar to the gravitational one, a different constant though, so it's 9 times 10 to the 9th for your constant. The different charges here. I've given you the charges in microcoulombs. That's what that mu means before the C. And so when we write this out, microcoulombs, micro means 10 to the negative 6th, or 1 millionth of coulomb. And so whenever you see that micro there, we're going to write it out this way. 1.5 microcoulombs is 1.5 times 10 to the negative 6th coulombs. All right, that times 2 times 10 to the negative 6 coulombs. Divided by the distance between them, 20 centimeters, that is 0.2 meters. And we've got to square that. Oh, I usually don't put my units in the calculations just because I think it gets a little bit full of things. So 0.2 squared here. And if you calculate that, you should get 0.675. Now I'll note there was a negative by the 2. That negative represents the fact that it's a negative charge, and then the positive is a positive charge. If the two charges are opposite from one another, that means that it's going to be attractive. So it's important that we know that this is an attractive force. If they were both positive or both negative, then it would be a repulsive force. That's the significance there. So I don't normally put the negative in the calculations, but if they're opposite charges, then it's going to be an attractive force, and if they're the same charges, you're going to get a repulsive force. This next one is a spring problem. For the elastic force, or for the spring force, we have FSP equals Kx, where K in this case is the spring constant, and X is the distance this spring is stretched or compressed. This one I kind of give the spring constant to you directly. That's 200. All right, and then how much it's compressed. It's compressed 25 centimeters, but we have to get that to meters. So we're going to say 0.25 meters. All right, and multiplying those by each other, you should get 50 newtons. Okay, this next one, talking about a buoyant force, so we have to use the buoyancy equation. The buoyant force is equal to gravity times the density of the fluid, which is this symbol rho, times the volume of the fluid that's displaced. So gravity times the density of the fluid times the volume of the fluid. So if we go through here, gravity is always 10, all right? That's the gravitational constant on Earth. The density of this stuff is 13,900. The volume is in the wrong units again. We need it to be in meters cubed because the density was given in meters cubed. All right, so what we have here then, 250 centimeters cubed. If you're going from centimeters to meters, you move the decimal place over 2 spots, but we have to do this 3 times because it's centimeters cubed and meters cubed. All right, so we have to move it over 2 spots for each dimension. So we jump over 1, that's 2 spots, and then 2 spots again, and then 2 spots one more time, and we end up with 0.000250 meters cubed. Okay, so times 0.000250. Go through and multiply those together. You should get 34.75 newtons. All right, this next one is a friction force. It says, what's the maximum static friction force? I will always ask you what the maximum static friction force is because basically if something's not moving, the friction force could be 0 if it's not moving. Think of just an object sitting on a table that's not being pushed at all. But the moment you start pushing on an object, it resists what you're doing to it, and it can resist that up to a certain point. That's when it would start sliding, and so I'll always ask you this maximum static friction if I give you the static friction. But generally speaking, we just need to know that the friction force is equal to our mu, which is our coefficient of friction, times the normal force. All right, in this case, mu equals 2.5. The friction force is 20,000. The normal force is 20,000. So 2.5 times 20,000 gives you 50,000 newtons. Onto the back here. This is another buoyancy problem. So we know the buoyancy force is equal to gravity times the density of the fluid times the volume of the fluid, so that equals 10 times 1,000. And then this is already in the right units. Everything's good in the right units, so 0.1. Right, and if you multiply all those together, you should see that you get 1,000 newtons. That one was very straightforward. All right, this next one here is a friction problem. It's a little interesting. So this is the only one that I give you where you have to do a little bit of extra work kind of on the side. It says an object has a mass of 45 kilograms. It's sliding across a level surface with a coefficient of friction of 1.3. What is the magnitude of the friction force? So in this one, the first thing you have to realize is that there are going to be 3 different forces acting on this object. There's going to be Fg in the downward direction. There's going to be Fn in the upward direction. Those are going to be the same size because it's not moving up or moving down. And then it's going to have a friction force that is resisting its motion. The gravitational force is related to the mass. It's equal to 10 times its mass. All right, so 10 times 45. which equals 450 newtons, which means that the normal force, because it's the same size as the gravitational force, is also 450 newtons. So then when we go through and we do this problem, the friction force is equal to mu times the normal force, which in this case equals 1.3 times 450. If you calculate that, you should get 585. All right, this one is another electrical problem. Electrical charges. One's positive, one's negative, so it's going to be attractive again. So Fe in this case equals, and then I gave you everything in the nice right units for this one as well. So it's that K Q1 Q2 over R squared business, which equals 9 times 10 to the 9th times 5 times -4, which I'm just going to call 4, and then we'll just remember that it's an attractive force here, over the radius squared, 35 squared. Put that in your calculator, and you should get 1.47 times 10 to the 8th. Right. This is an incredibly large force. So the reason I did this one was to show you, usually charge is measured in microcoulombs. A coulomb of charge is actually an incredibly large charge. And so if we have these objects, which 35 meters is like across a very large room from one another. And so these two objects are across a room from one another, and they're charged. And the force between them, I talked about it in one of my classes, is something like the same as the weight of like 7,500 cars. All right, so it's like an incredible, incredible force. You wouldn't normally get two objects that were not like large objects, like planetary objects that have forces this large involved with them. So, it's very, very big. And it's because I used units of coulombs here instead of microcoulombs, and that's why microcoulombs is definitely more common. It says, is it an attractive force or a repulsive force? One of these things was positive, and the other one was negative, so it's going to be an attractive force. All right, number 9. This is a spring constant problem. It says it requires 1,500 newtons to stretch a spring 10 centimeters. How much is the force required to stretch the same spring 0.55 meters? Well, this is a two-step problem. The first step is we have to figure out what the spring constant is. We know that for springs, it's equal to kx. All right. As the first part here, it tells us the force. It's 1,500 equals. We got to figure out what that k is because we don't know what it is for this spring. But it says it's the amount needed to stretch 10 centimeters. 10 centimeters is 0.1 meters. Okay, so if we solve for k here, we get k equals 15,000 newtons per meter. All right, so that's the first part. Now it says we're going to use the same spring in the second part, and it's asking us how much. So the next part then we'd say FSP again equals, in this case, we're going to use that same 15,000. And then this time we're going to say times 0.55 meters. And if you calculate that, you should get 8,250. Alrighty. This last one here is kind of two problems wrapped into one. I told you to compare the forces for these two objects. The first one here I'm going to do is an electrical force. So we've got Fe equals K times Q1 times Q2 over R squared, which equals 9 times 10 to the 9th times, and then this is microcoulombs again, so in the top I've got 30 times 10 to the negative 6th times 50 times 10 to the negative 6th over the radius squared. The radius given here is 50 centimeters. Got to get that in meters, so it's 0.5 meters, and that needs to be squared. So I do that, and then I get 54 newtons for my answer. Now I'm going to do the gravitational force between them. So I've got Fg here equals g times m1 m2 over r squared. In this case, that's 6.67 times 10 to the negative 11th. That's the constant g. Times the mass. It's 30 grams. We got to get it in kilograms, so 0.03. And 50 grams is 0.05 kilograms, and divided by the radius squared, 0.5 squared. All right, and if you calculate that, you end up with 4.0 times 10 to the negative 13th. Okay. Something to mention here. They're both positive. The charges are both positive. So on that electrical force, if the charges are both positive, this is a repulsive force. Gravity, on the other hand, is always attractive. The other thing here is, if you're comparing the size of them, you see that the electrical force in size is always going to be a lot larger than the gravitational force. This is because gravity is, generally speaking, a very weak force. So you have to have a really, really large object for gravity to matter. So the gravity is almost nothing. The electrical force here, though, between these objects is sort of substantial. It's 54 newtons. So it's, you know, it's definitely much larger than the 4.0 times 10 to the negative 13th newtons that we have for the gravitational force. I know this was all pretty quick. If you have any question on these force problems, make sure that you stop in and ask. There'll be a quiz on this coming up, so and then it will be on the test. So just, careful about that and make sure you're keeping on top of things.